Hello and welcome back. This is Mama J with Science with Mama J. I would like to welcome you back to our first recording of the school year. This is to help review for checkpoint 1 for the 8th grade test that's coming up. I had a few concepts that I wanted to review to help make sure you understood what was going to be on your test, or the concepts that were going to be on your test. The first concept I wanted to cover was contact versus non-contact forces. Okay, you have your basic push and pull force, you have your frictional forces, your normal force. For example, if you're sitting on a chair, okay, you sitting on a chair is providing a normal force onto the chair. Okay, frictional forces, for example, if I were to push this table, as I'm pushing this table this way, the frictional force is applied in the opposite direction of the direction of my push, which is why it's a little bit harder. The heavier the object is, the more friction is going to impact your ability to push the object. Okay, you do have some non-contact forces, such as electrical currents, and you have magnetism. For example, now when it comes to these non-contact forces, they are distance dependent. So for example, I have a magnet here and another magnet here, and hopefully you'll be able to see this, but right now it doesn't feel like much is happening, and as I get closer, I can feel that something happened, and the closer I got. Now I'm actually going to turn this over, because since they're magnets that are designed to stick to the wall, here you have the magnets. They jump up the closer you get, and the further away you get from the magnet, I actually have the magnet that came off here, the further away you get from the magnet, the less impact it has. The closer you get to the magnet, it immediately pops up. So again, non-contact forces are distance dependent. The closer they are, the stronger they are. Air resistance. One of the forces we talk about is air resistance. So for example, let's say you see someone jumping out of a plane, okay? When they're falling flat, that person is going to move slower than, let's say, if they were falling at a 90-degree angle. So if they were horizontal, they're going to move slower than if they're falling at a 90-degree angle. Now, if they open up a parachute, okay, now this parachute is coming way across, they're going to fall even slower, because that parachute is now going to increase the amount of air resistance that person is experiencing as they're falling towards the earth. So the purpose of a parachute is to actually slow someone down and allow them to steer a little bit as they're falling towards the earth, so that they don't hit the ground too hard. So forces such as magnetic forces, okay, and let's talk about electrical currents. For example, these forces, like forces, will repel each other and opposites will attract. So for example, and it may be hard to show with these, here, if you notice, it's attempting to flip the magnet and it keeps flipping it because the like poles are actually on the opposite sides. So this pole is opposing to this pole, or is like this pole, so it's going to oppose it. So positive and positive charges will repel each other, negative and negative charges will repel each other. North and north poles of a magnet will repel each other, and south poles of a magnet will repel each other. So you'll see here, it's trying to flip the magnet, which it did, to get it to the side that it wants to be on. So if you look again, and you'll see, I don't know if you can see the magnet moving, and then ultimately it flips over. Okay? So, mass versus weight. This is a very important concept a lot of students struggle with. Mass is the same anywhere in the universe. Okay? So if something has a mass of 10 grams on Earth, it'll have a mass of 10 grams on Mars, it'll have a mass of 10 grams on Jupiter, it'll have a mass in 10 grams somewhere else in another galaxy, in another solar system, in another part of space. It will always be 10 grams. However, weight is dependent on gravity. So an object can have a certain mass and let's say weigh on Earth 18 pounds. But on the moon's gravitational pull, because the moon is much smaller than Earth, its gravitational pull is 6 times less. So instead of weighing 18 pounds on Earth, on the moon, it's only going to weigh about 3 pounds, 6 times less. So your weight will depend on where you are in the universe. Okay, on the moon it'll be less, on Jupiter it'll be more, on Mars it'll be a little bit less than Earth, so on and so forth. So weight depends on the gravitational pull where you are, but mass is constant and it never ever changes because mass measures the amount of matter, whereas weight measures the effect of gravity on matter. Okay? Theories versus laws. A lot of students struggle with this concept, but it's actually pretty simple. A law simply states what it is. And of course, we're talking about scientific laws here. We're not talking about actual man-made laws. A scientific law is a law of nature, okay? If I were to take a ball and I were to throw it up in the air, the ball is going to come back down. That is a scientific law. It is what it is. It just simply states what is happening in nature, okay? Whereas a theory will seek to explain why or how it happens, okay? So a law simply states it. It is what it is, but a theory seeks to explain why or how, okay? So gravity and planets and the sun. So when we're talking about gravity, we're talking about the planets, we're talking about the sun. Okay? First of all, we have gravitational forces, and I want to talk a little bit about gravitational forces before we get into the planets and the sun. So here, this only shows distance, this doesn't show size. We'll talk about size in a moment. But here you'll see the distances, okay, between them. So we're going to show the force vectors for A and B, okay? As the force increases, these vectors will get longer. As the force decreases, the vectors will get shorter. So if you notice, as we bring these together, the vectors got longer. The closer they get together, the greater the gravitational pull. Just like with the magnets, the gravitational pull, as you got closer, got greater and greater. As you get further and further away, the force gets less and less, okay? So the closer two objects are, the greater the gravitational pull. The further away they are, the smaller the gravitational pull. Likewise, the bigger an object is, the greater the gravitational pull. The smaller the object is, the smaller the gravitational pull. So the least gravitational pull will occur between two objects that are very far apart. The greatest gravitational pull will occur between two large objects that are very close together. Okay? So if I had, let's say, two objects that were this distance and they were small, they would have a smaller gravitational pull than two identically or equidistant objects that were much larger. Okay, let's say twice the mass. You would still have a gravitational pull that was greater between those objects than the tiny objects. Okay, so when it comes to planets and gravitational pulls, when it comes to how they orbit, so let's go ahead and pull up planetary orbits here. Oh, I would need my keyboard. Okay, hopefully this will give us what we need. Oh, these just show orbital motions. Well, we could probably use this. So when it comes to orbital motions, okay, first of all, it's important to understand how orbits work, okay? An object will go in a direction that it was originally going before something interferes with it. So an object at rest stays at rest, an object in motion stays in motion unless acted upon by an outside force. Well, in this case, this object was originally traveling in this direction, but it got caught in the sun's path. Because it got caught in the sun's path, it's continuing to try to go in this direction, but it's getting pulled towards the sun. Now you'll notice it has a very strict elliptical pattern here. Okay, it's further away over here, it's getting closer together, so the gravitational pull is greater. Now, if we were to move it, okay, I can't get it to move, let me reset. Okay, if we were to move it away, now you'll see it moves slower. Okay, it's further away. The gravitational pull is much smaller, showing the further away you get from the sun in this case. Okay, but as it got closer here, because it is on an elliptical pattern, you did see that green arrow shows the force of gravity. You did see that it did get a little bit longer. Here it got very short because it's the furthest away. As it gets a little bit closer, you see that arrow gets bigger. So orbital patterns occur based on gravitational pull. So when we look at something like our planets, well, we have 8 planets in our solar system, okay? The planets closest to the sun, you'll notice, are much smaller than the planets further away from the sun. The reason for that is because those small planets are rocky, denser planets. They're able to maintain their orbital patterns because their mass and distance from the sun balance them to keep them in the orbit that they are. If you were to take Jupiter, for example, and you were to put Jupiter in Earth's orbit, Jupiter would be too big to maintain the orbit that we maintain, and it would get pulled into the sun. Because its mass, as well as the distance, is important. And Jupiter is actually our largest planet. Okay? So, the geocentric versus heliocentric model. This is actually really important. Okay? The geocentric versus heliocentric model. I'm hoping we have one here. I don't know that we actually have a geocentric versus heliocentric model. And we don't, sadly. Okay, so we'll talk about it without using this. A geocentric versus heliocentric model, if you think geo, okay, geography, rocks, we're studying how the Earth, geo, is positioned in the center of the solar system. And that particular model, because the Earth is positioned in the center of the solar system, everything is orbiting around the Earth, to include the sun. The heliocentric model, on the other hand, which by the way is how our solar system actually works, is the model that shows the sun at the center of the solar system. So with the sun being at the center of the solar system, everything orbits around the sun. Okay, so the two models show different orbital patterns. I would love to show you the orbital pattern of the Earth, or of everything around the Earth. It's actually a very complex pattern to be able to explain what we see in the sky, but it was the reason why the orbital pattern, the geocentric orbital pattern, was debunked, because it shows that it really just doesn't work. The heliocentric pattern with the sun in the center of the solar system actually is able to be explained much more easily. It shows how everything actually moves, and we're able to see all of the planetary movements, the constellations, and everything much, much better given our planetary movement. So, but the difference between them is geocentric is Earth-centered, heliocentric, sun-centered. So I think we may have covered all of the topics. I think we've covered all of the topics that I was concerned about for this test. If you have any questions, please feel free to come and let me know. And good luck preparing for your first test of the year. Take care.